So welcome back. So we were left at measuring our maximum function comparing to the factory or the built-in function. So my function is basically gets slower roughly by the same ratio as the built-in function, right? So basically in rough terms, it's roughly as good or complex, or its complexity is as good as the official function, right? Because it seems, at least, well, that's a hypothesis, right? You still have to prove it, right? But it seems very likely because, again, 10 items, right? Same ratio. It's linear, right? So it's most likely also both these functions are, the complexity is linear, right? Because we'll talk later on, it's called actually ON, right? The big O notation. But for now, yeah, it's linear. So it's basically because it makes sense, right? Because you have n items, you have to go through all of them once, right? You don't have to do anything else, right? So that's your basic unit of comparison, right? If you see a loop, you do something once, right? Then that's most likely it's a linear complexity. That's very informal right now. I'm not like you don't have to, be completely pay too much attention at the moment to this. So, right. So let's try this 10 million items, right? So up to 1 billion, right? And let's see how well it works now on 10 million items, right? First of all, it takes a while to build this, right? I'm actually surprised that Google has not shut me down. I guess it seems that it's okay. Let's check if I have variables. How many variables do I have? Yeah, I have all of them. Yeah. So the kernel is still running, right, on the Google server somewhere, right? So it looks okay, right? All right. So I have 10 million, huge list, 10 million items. So what's speed? What's the speed? What's expected time when I'm going to run right now? I have 10 million items, right? What do you think? If the big list was 19 milliseconds for max, built-in max, and 85 milliseconds for my function. So we have 10 million items. What do we expect roughly the speed? Yeah, something like 190 to 200 milliseconds for the backs, and maybe 900, maybe a second for my function. Maybe we'll see, right? We'll see. So I'll time it. Right. Again, this is the old number. We'll see this time on the Google servers. Oh, pretty quick. So question now, why was it so quick actually? Well, yeah, it ran only 7 times. Right? 7 runs, 1 loop each, basically, right? So it only did 7 times, right? Because why? It figured out this is slow. This timed function has certain, has a certain limit of time limit, basically. It does not want to spend too much time doing something, right? So if the function takes a long time, it will run it only, the least it will run is 7 times, right? So you have, 170 milliseconds plus 4 milliseconds. So if you see something like this of course, statistically speaking, this is not very significant, only 7 runs, right? There could be some things happening, maybe you run it 50 times, some weird stuff starts happening. 7 runs is still not enough, but it's a good, good starting point, basically, right? If you have like 10 million loops, right? That's probably pretty accurate, right? Right. So, okay. So, like you said, it's roughly within what we expect. How about I expect also. I'm gonna guess about 870. I don't know. We'll see. Maybe less. Maybe it takes longer. No, exactly, 816 milliseconds, right? So now, right, we went from 1 million to 10 million items, right? And still the ratio, this linearity stays, right? So again, both functions are basically, as far as algorithm researchers concerned, right? They are most likely the same complexity, right? Meaning they have same sort of performance. So now the question, of course, is, same performance, but why is my function slower always by the same amount, right? What could be some of the what could be explanation? Let's think about it. Why is my function it's slower, right? 3 or 4 times slower, no matter what, basically.
You declare, like, you have to put the values into variables, while
yeah,
the built-in function could use pointers.
Yeah, basically, yeah. The explanation again. This is not something. Somebody could write a research paper actually how Max is implemented. You can find the source code on GitHub, Python source codes on GitHub. Most likely, I'm almost 100% sure that Max is actually written in C, right? Compile. It's already optimized. Basically, I mean, the optimization is basically, I am writing my Max function actually written in Python, basically, right? But the Max, since it's used so much, all right. It's very similar code, but it's written in C because Python usually is written in C itself, right? So it's already pre-made, basically, right? Maybe there could be some tiny system-specific differences, basically. But yeah, it's not. It's basically some system, sort of like some sort of tiny hardware optimizations, basically. And also, of course, depends on the language, right? As you probably know, Python is not a fast language, right? But Python is extremely fast if you use many of the built-in things which are written in C, actually, right? Many of the libraries, such as NumPy or some numeric libraries, are much faster than the, let's say, working with lists. Because why? Because it's written in C. Actually, the actual hard work is done by the compiled, dynamic library, basically, by the library. So, yeah, but it looks like, again, as far as complexity, my code is not as bad. It's just as good as this Max, and I would like to think if I could write my own C extension, which you can actually, right? It's not that hard, right? For Python, right? My function would be very close to what this Max function does, right? So, okay, now. We could probably, I wonder again, maybe someday, we could do we had some extra time, we could find actually the implementation somewhere. There should be like a maxc file somewhere in the Python source code, and you could probably find it. Right, so now the question is, can we find the max or min faster in a list? And again, if you remember your Harvard course, you probably will think of this. How can we do this? Right, so let's do a sorted list, right? So sorting, we'll cover sorting a little bit later on in this course, but we have a built-in function sorted, so we'll have a sorted big list, right? Right, we have how many items? We have 1 million items, right? And we're starting with 102, right? So how about finding max in this list, right? Let's do, it's 1 million items, right? Big list, 1 million. Well, will it be faster? 95 milliseconds, and before we had 180. Oh wait, I forget now.
130.
Yeah, no, that's yeah, 100. Yeah, sorry, big list, 1 million. That's not huge list. And actually, a max big list. Yeah, it's actually slower now. 19 milliseconds. It's interesting, actually. Sorry, but
Because it.
yeah, no. Let's think about it. Well, yeah, 100. Minimum. Let's find the minimum, right? But of course, this is a trick question. So, how could I find a maximum in a sort of big list? No, yeah, of course, right? And how about the minimum? Take the first one, right? So yeah, so this was like using a max on a sort of big list is kind of silly, right? So we can, I think I'll have this, right? Yeah. So if I could do this, right? Obviously that works. But so how about this function, right? This is the last item, so the max, right? Yeah, 50 nanoseconds. So again, it's like a atomic. It's like the tiniest, it's the simplest thing we could think of, but it still takes 50 nanoseconds, right? In Python, right? Getting the last item from this list takes 50 nanoseconds. So again, it seems very fast. That's 50 billions of second. But if you think about it, it's not too fast. Why? Because how fast are our computers? What do we measure speed in? What's the speed measurement or CPUs? What's the measurement usually? What's when you buy a CPU, you go to, if you look at your specs. Okay, well, let's look. Yeah, hertz, yes. So G, gigahertz, right? So what's giga? A lot, right? So let's look at this. Mega is million, right? So giga is billion, right? So billion operations, right? So it's 9 zeros, right? 9 zeros, right? So 3 billion operations. This is not a fast laptop, right? But again, if you look at the hardware, it usually stays now. You can get like 6 gigahertz now, up to 6, but it's not going up. Physics, we're staying around 6 gigahertz for a while, actually. 5, 6, that's really good. 3, 4 is still fine, right? But anyways, what does it mean is that a single core of a CPU, right? Did you take a CPU hardware course? No?
Yes.
You did, right? Okay. So single core, right? It does 3 billion operations, right? Roughly speaking, this is really simplistic right now, right? Just one core, right? I have like 6 cores here, but one core, right? Python is single core. So you could do theoretically, right? Getting, you would think getting the last item. Well, it shouldn't take. It seems like it took like about 100. It said 15 nanoseconds, right? So it's about 150 times. The computer did about 150 operations. 3 gigahertz, right? So 1 billion operations. If we had a 1 gigahertz speed, right, and one operation was needed, it would be 1 nanosecond, right? But it took about 150 operations to do this, actually, right? Why? Because, of course, Python is running on some server, right? There's OS, there's an overhead, there's a bunch of abstractions, right? The calls, right? So lots of extra work being done, actually, right? Do this, right? And of course, you have to do a memory access. Actually, also, it doesn't take like one operation, maybe it takes a couple operations, right? Maybe if you did this in assembler, right? Machine language, maybe you did this, maybe you could do it faster, right? You probably could, right? So how about finding my max now? My function, how will it work? Yeah, 200 nanoseconds, right? Yeah. So about time, actually, yeah. So again, last sort of big list, right? Yeah. Same thing. 50 nanoseconds should be. Yeah. So this is what's called O1 time, right? So no matter if I have something, if I have fixed, I know where things are, right? I just go look it up. It doesn't matter how big my list is, right? I can always do it. Even if I had billion items, even if I had trillion items, well, my memory, I would run out of RAM, right? But still, let's pretend I have terabyte of memory, right? It still takes same time, right? You know where to go, right? Doesn't matter how many items. So this is O1 time, again, right? So now the question is, we want to find, we're going to generate some numbers, right? Right, n in big list for n in range 9000. Okay, yeah. I'm gonna generate some numbers. Right. So what I'm gonna test is right now. What did I do here? Right. I'm testing. First, I'm gonna check if some number exists first. Right. False. Yeah. I think. Yeah, 129. So only one number. So let's check which one it is. So looks like 9129 is in my big list, right? It's just a number, right? So how long? So it's called existence check. I will add this here. Code existence check. Existence check. So I want to check. This is actually often a standard operation in most languages when you're learning about programming languages. Finding if something exists, right? Existence check, right? So whether this item is in a list, right? In an array, right? So existence, no, that's wrong. I can spell, right? Existence. Wait. It's correct, right? Yeah, okay. I don't know. Again, it's morning. So, still morning. So, 9129, right? So I'm checking, right? In a big list, right? Whether it exists, right? Remember, this is not sorted. Big list is not sorted. 9 milliseconds. So how about sorted list? Right? You probably know thinking what's going on here, right? Let's take a look. 1 microsecond. Okay, so what's faster? 9 milliseconds or microsecond? Yeah, so this is 1 millionth of second, right? And this is 9,000 of a second. So this is about 9,000 times slower, actually, right? 9,000 times slower, actually, right? So question to you, why is this faster? Why is the sorted list, why is this finding, okay, remember I'm returning it true or false, right? I'm just checking whether this number exists. I know it exists already, but I am checking, right? So why does checking here takes 9,000 times faster?
You don't have to go through everyone.
Yes, you exactly. What's happening? This in, remember, this is basically a function, right? In is a built-in Python function, basically, right? It goes through. If it finds something, it doesn't have to go through the rest of it, right? So what's happening if you have an unsorted list, right? I'm gonna guess this 9129 is towards the end, probably somewhere in middle, maybe. Let's find out exactly. I don't remember exactly where it is, but it's probably in the end. But 9129 is probably somewhere in the beginning of sorted list. Almost surely it's in the beginning, right? So let's take a look at the indexes, right? So yeah, exactly what I was gonna say. We're gonna check index of both lists. So this one is gonna be, yeah, it's 891,000 something, right? In an unsorted list, but it's only item 94 in our sorted list. So obviously, well, what's the ratio, right? Let's do this. Yeah, exactly what I was gonna do. I'm gonna divide the ratios. So it should be about 9,000, right? Or 10,000 roughly ratio, right? So, yeah, about 9,000, right? So, so that explains this, right? This in has to do about 9,000, has to go through about 9,000 times less items, right? So it explains the speed, right? The difference, right? Finding something. If you because how would you write the algorithm to find something? You just start at the beginning and go to the end, right? Right? Okay. All right. So we'll see. Yeah. So again. So this is explanation. So hopefully every is clear. Why it takes so much faster in this particular case, right? Right? Index in 94 because 9 times it's at the beginning, right? So last 5 items, right? So let's check, right? So now, yeah, I'm gonna sort it, but I'm gonna look for the very last item, right? I want to check if very last item exists, right? And now, well, what's gonna happen? It's gonna be extremely slow because it's the very last item, so it has to go through. It keeps okay. What's happening? It has to keep check, and finally the last item exists. Okay, it returns true, right? So 60 milliseconds. So it's very slow, right? Very slow. How about big list, right? Why? So now we'll see. It should be faster again, because it's about 10 times faster. So my hypothesis would be it's most likely because when it's unsorted, it's probably somewhere maybe not very beginning, but somewhere early part, right? Maybe like 100,000 something, probably, right? Let's check, right? Yeah. So of course also finding it if this number does not exist, right? This number doesn't exist. It should be very close to this number, right? In a big list. Actually, it keeps. Oh no, big list here. Yeah, right. So it takes longer, right? So, so again, finding the index, right? Yeah. So this number was in the middle somewhere, right? And here it was very last item, So now, yeah. So this is all building to what I'm. Can we do better? So can we do better? If I want to find if something exists, right? I have big array or list of numbers. Can I do better than going through one by one, right? Yeah, that's what I'm getting at, right? So if I only have unsorted numbers, if I don't know anything about these numbers or items, right? Well, if you can think of something, maybe you'll find the prize, Turing prize. But no, most likely no, we don't know of any way if we have unsorted numbers. But we have sorted. What can we do? Yes, exactly. Yeah. So you guys already saw this. You like it because it was. I think it's covered. Harvard course covers this as well. All right. So binary search, and this is one of the underlying ideas. Right. It's like one of the basic tools should be in your arsenal. This binary search. It works everywhere. Like, let's look at this here. Right. So first of all, I will show you a couple of things. Can we do better? Right. In unsorted list, we have to spend O(n) time because we have to check all items, right? Actually, the best way to check, there is even a better way actually. First, yes, we'll get to binary search. I'll show you the best way to do it, right? But this has a big disclaimer, right? We'll later on we can use a set, which is basically a hash map, right? Hash data structure. We will cover in data structures course, right? And we can check this instantly actually. Yeah, turns out we can do it instantly. This is the best way of finding things, right? But there's a big downside to this, right? So this is 70 nanoseconds, right? We can find anything, even if something doesn't exist, right? It should be very fast, right? So big set data structure, right? Very useful. I don't know if you covered this in Python class. You probably covered sets a little bit in Python, right? You did. Yeah. So you're fine. So sets are great if you need to do a lot of membership testing, right? What's the downside, of course, is you have to build this set, right? You have to build another data structure, so it takes memory, right? And it takes some time to build it up. It turns out it takes linear time to build up. So if you're gonna check for something, right, you say, okay, I'll use set, it's fast, it's all one, it's constant time, it's very fast. But the downside is this operation will take linear time, so you just sort of pass the cost, right? You have to do it at some point. So this could be an option if you can pay it first, you pay this extra cost, this computation cost, right? At the beginning of your program maybe, but later on, people will be doing a lot of lookups, right? Later on, right? This is the idea behind indexing in databases, by the way. In many cases, right? You pay something, you pay this extra cost, computation cost in the beginning for indexing, building these hash maps, but later on, you can do these fast lookups, right? So it's one of also another tools. Yes.
Can you show like time it function of
this one?
Yes.
Yeah, let's do this. The only question is now let's do this. Very good idea. The thing is, sometimes, of course, with time it is things is sometimes what is we'll see if it's 200 milliseconds, right? So pretty slow, right? First of all, you have to have memory, right? So yeah, so we actually lost time, right? Again, so set makes perfect sense if you know your application, your program will need to do a lot of lookups for these items. Existence checks, then yeah, you set aside some memory for this set, and you spend some time beginning, right, while people are loading up the screen or something. But later on, you have big performance gain, right? So, but again, but here, if you only do one lookup, it's not gonna make much sense, yeah. So so sets are the best, but yeah, so choosing a right data structure can be crucial, right? So list is ON, set is O1, but we get to now to the binary search, right? So right, so here's a little aside before we get to that. What was I trying to do here? So count 100,000. Oh yeah, right. So also this is an example of doing something bad, right? Let's see. Oh, yeah. Let's see 100,000 items. We don't know. We are like Python beginners. We don't know about list comprehension, right? And we keep appending numbers, and then we reverse the numbers. We want the reverse list, right? Silly example, right? So it'll take 7 milliseconds, and here it'll be much faster, right? But if you know about these things, right? Yeah, 3 milliseconds, right? Yeah. But you say, okay, yeah, so these seem pretty fast, right? Yeah, right, reverse, you want reverse list again, of course you could do a reverse, right? This is probably the most Pythonic way of doing it. But you are like, say, okay, I'm gonna start inserting, you want a reverse list, I'm gonna insert in the beginning, right? So this is gonna be horrible, right? And this is actually probably translated to the next lecture on data structures, right? Inserting things at the beginning of a list is oftentimes a bad idea. Does anybody can think of why? Yes, exactly. It has to push all the stuff, right? Depends on the data structure, but this is a huge difference, right? These two, right? This Pythonic way or even this naive way, right? Both of these were like in the millisecond range, right? But here, this took actually 3 seconds. And I can tell you, if I did 1 million items, yeah, it would be not 30 seconds, it would be 300 seconds, it would be quadratic time. It would take, because why? Because this insertion, this is, so this hides linear complexity for insert, right? Because we're inserting something beginning, we have to move things. So you have to be very careful with these things. So knowing about your data structure properties. There are some data structures, we'll learn about them later on in another course, that actually you can insert things in beginning, right? You have to look at your language documentation, see, does insert, is it a linear, is it a constant, right? Maybe it's something else, right? So yeah, so this quadratic complexity. But now I want to get back to, before we finish the lecture, to finding the needle, yes, to binary search, right? So this is my implementation, is needle in sequence. So I have a sequence, I have a needle, right? That's what I'm trying to find, if it exists. I want to return true or false, right? So how do we implement this, right? So sequence, I have a documentation, a doc string, that it should be sorted and indexed, right? Otherwise, this will not work, right? So let's look at this implementation, right? So we start at beginning, end is your last item, right? It's zero-based indexing, right? So this is this is basically a binary search. We start at beginning, right? While start is less or equal to the end, and we find the middle item, right? Remember, this is integer division, right? Without floating point, right? So if our needle is the middle item, we win. We already found it. We are finished, right? That's a best case scenario. But what happens if it's not found? Well, we need to check whether our item, we know it's sorted, whether our needle is bigger than middle, right? Or less than middle, right? So if it's bigger than middle item, we're gonna start at one after the middle item, right? Because we know it's not middle for sure, we need to check the next one, right? The start. However, if it's less, then it means we have to adjust the end to the one less than middle, right? So if you had to do binary search in a programming interview, you probably could do it now, right? But it's easy to mess up with this one-off index, right? It's very easy to mess up, right? So, and again, so also, if after we keep, like we have this needle, right? Start somewhere here, right? And we keep going, right? We have our needle here, so we have like maybe, I'll do like 1, and I don't know, like 9, 9, 9, 9, 3, 8 or something, right? And we're looking for like, I don't know, 9,000 something, right? 9,000, that was 129, right? It's somewhere here, right? Right? And so middle is probably like something like, I don't know, roughly like, I don't know, 490,000 or something, I don't know, right? So that's a middle, right? Mid, right? So yeah, so we keep dividing. Maybe I need to do this. I see a teacher who does like three marker technique, right? 3 markers in one hand, right? So mid, and then mid, right? And then mid, right? And eventually, right? So, right? And we eventually, right? We converge, right? So, and so the question is now, is this going to be linear? No. Yeah, why? Because we keep decreasing the search space by half, right? So this is going to be logarithmic. Yeah, exactly. So you pretty much learned this course already, right? So you have to remember linearity, logarithmic complexity, and constant time. So those are going to be the main sort of like units or like building blocks of complexity, right? Constant, logarithmic, and linear, and of course you build on top of that afterwards, right? So yeah, so this is, in many cases, this is best we can do. In some things, like if you can somehow get this this problem search space can be divided in half, sometimes in third, maybe sometimes could be 2/3, right? It doesn't have to be exactly half sometimes, right? But the idea is, the basic idea, if you can, so do better than linearity, basically, right? Because you're dividing the search space. Okay, so this algorithm, right? Let's run it. Let's see how good is it. Again, my prediction is it's gonna beat a linear search. It's gonna beat linear search. It should, right? It should, right? Is needle in sort list? True. True. And let's time it. Remember, this is 1 microsecond, right? And how about my? Yeah, 7 microseconds. So the question is no. Yeah, is it my actually seems like a little slower. It's a binary search, right? So one of the things is sometimes optimized linearity, right? Might be better. I can beat this binary search on some unoptimized implementation, actually, right? Because we already know in does not know if it's sorted, right? But it is written again in a low-level library, right? So going through a brute force search actually might beat this sort of optimized, this optimal algorithm. Like sometimes a very fast implementation of slow algorithm can beat a slow implementation of a good algorithm, actually. Right, but let's check it on something which is not in a list. Let's check it. Like this number does not exist, right? 6 microseconds, so that's a good. Yeah, final, you see the big difference. Okay, so remember here, right? Why was this fast? Because this was at the very beginning, right? So it went through like the first, it was like 900. Excuse me? It was very beginning, right? Yeah. So it went through very quickly, going through array, right? Low level array in memory. It's usually in the same contiguous memory, right? So it's very fast operation in a low level CPU operations, right? So it went. It actually beat this binary search, even though we did maybe we did less operations, but we had to do some jumps in memory, right? Going in modern CPUs, going through sequential memory is very fast. Why? Do you know anyone about the hardware? This goes back to the hardware course. Your CPUs have what? What's inside CPU? Well, you have some registers, short-term memory, right? It has some CPUs have some operations. You know, adders, multipliers. You know, some decoders. Some modern ones have decoders for doing like 500 operations at once. But it has some operations, some basic arithmetic operations. It has some some jumps, conditional jumps, right? But also modern CPUs, most of them CPU space is taken by what? Anyone know the answer? Yeah, transistors. They're all built on transistors. Yes, but what do these transistors do? Mostly CPUs. And I'm going to set aside the graphical part. I mean, some CPUs have graphics inside, but that's okay. But just CPUs. If you think about it, what's inside? Let's look at. Let's see. Let's look at this. Let's look at. I don't know. Let's show again. I guess AMD Ryzen. Let's see. 99X. I don't know. 9X layout. Let's see. Maybe add this a new chip, right? Images. I want to see some images. Come on. Where is it? Maybe I need older one. Right. But this one here. Okay. Let's take a look. Right. Okay. Right. But this is not a very not actually. It's even worse than that. Actually, you see the cores, right? There's an 8-core CPU, right? So actually 8 CPUs inside one CPU, right? 6-core actually. 6-core. 8-core. Alright. So anyways, but you see here this part here, right? This is cache. This is actually RAM. It's actually memory, but you have cache memory basically. Right? So now these days modern CPUs have 3 or 4 levels of caching, meaning you have some registers. You maybe have 8 or 16 or maybe I don't know 64 values you can store next to your adders. But then you have caching memory, meaning, and it keeps getting slower. Like the RAM, the gigabytes of RAM we have in your computer, they are on separate chips, right? Right? So the closer you are to the CPU, the closer you are to operations, right? where stuff happens, right, the faster it will be. Latency, like how long it takes to go from your instructions, your data, right, has to travel to the actual work being done, right? So what's happening actually is modern CPUs are very optimized, so they make a lot of assumptions. So let's say you have some memory, right, and if you start looking at some number, right, and you have a loop, right, it's in low-level language, it goes through, it will actually start predicting, oh, you probably want to get the next number too, and next one too. So it'll start reloading this in a pipeline, sort of like doing all this work, assuming you want to look at the next one, next one, next one. So looping through some like basic sort of arrays list is very efficient in modern CPUs, because what's happening is it's doing all this work even if you didn't ask for it, right? It's building up this pipeline, right? So, and many times it turns out you actually do want the next number and next number. So when you load this first number in memory, right, it actually loads the next ones too. So it does a lot of groundwork, preparing work for looking up the next numbers, right? So, and oftentimes, right, this is called branch prediction. It kind of expects CPU, sort of tries to predict what you're going to do. It thinks, okay, you can do a simple loop through some numbers, right? And it's often what you want to do. So in this case, actually, right, this operation actually was very, very efficient, like brute force operation, right? It was preloading in your CPU, right? And this has been true for the last, I don't know, 10, 20 years at least, right? So simple loops, actually, starting with simple loop is not the worst case, not the worst thing to do, right? But eventually, of course, bad algorithm will lose. This is one takeaway from today's lecture is eventually, right, a bad algorithm will lose. A bad algorithm in a fast CPU on a fast computer, right, will lose to a good algorithm on a slow computer, right, on a slow language, right, eventually. The only big question is when will it happen? Will it happen at 1,000,000 items, maybe 1,000, maybe at 10,000, 50,000, maybe 50 billion, right? Sometimes, researchers find a really good algorithm. It's a great algorithm. It beats like things. But the only problem is you need like 100 trillion items to actually have an improvement over an older, simpler algorithm, right? So that's another takeaway from today, right? Sometimes a bad algorithm will beat a good algorithm, actually. Okay, but let's before we finish, right? We should be finishing, right? So I want to see if I can find. So my needle for my binary search beats built-in regular brute force in, right? So my smart algorithm beats it, and it's logarithmic, right? Because it divides by half, by half, by half, by half. It's like the children's game, right? You guess a number, right? The strategy for guessing a number, right? One person thinks of a number, right? The strategy is divide by half, by half, by half, right? Did you guess to 50, right? Then guess 75, 88, right? And then you divide the half and half and half and half, and you find it, right? That's the optimal strategy, right? Okay, so GCD, you don't have to worry about it. That's another old algorithm, right? So today's takeaway. So we have our basic constant time lookup. If you know where something exists, you have a logarithmic time, right, which you just looked at. And of course, linear time. So linear time lookup, going through something with a loop is like your basic building block. That's what you start with. And in this course, oftentimes we'll see if you can do better. And sometimes you need to do a loop within a loop, of course, right? That's for following lectures. So, any questions? So, question is now, okay, do you have anything to do today for this course? I don't know. Let's check. That's a good question. Let me save this copy in GitHub. I'll update. Well, I think I gave you a quiz or no? Let's see. For today, for first day, I don't think I gave you a quiz. Yeah, so you're lucky. Today is no quiz, but on Thursdays there will be a quiz, right? On recursion, right? So today, relax. Yeah. So any questions on today's material? No? No? Were you able to follow? Was it too fast, too slow?
All right.
All right. Okay. All right.
Question.
Yes.
Do you need to read some material for
Well, for the next week, so you do the quiz after the class, right? So if you want to, you can read look at the notebook. If you want to prepare, you can go to the notebook ahead of time, right, and see what you're gonna do if you want. But it's not required. Right. Yeah. All right. So I'll see you guys in 20 minutes, right? Yeah. 30 minutes actually. Oh, plenty of time. Get breakfast or I don't know, lunch.